Probability in the normal curve. Okay, this section is going to introduce you to a very basic fundamental concept that deals with the shape of a very characteristic distribution. And this distribution is extremely important. It's used as the basis for calculating standard scores, and it's used as the basis for calculating the probability that certain patterns could have occurred by chance or not. Statistics is about defining a pattern using numbers, and then deciding if those patterns could have occurred by chance, did it likely occur by chance, or did they occur because of design, of some feature of the environment that's true and valid. Well, to calculate those probabilities, you're going to be using the normal curve. The normal curve is just a bimodal symmetrical distribution like you see in the slide. It's also called the bell curve. You may be even familiar with it by that name. It's the basis for all of modern statistics. And whether that's good or bad or not, it's hard to say sometimes. Unfortunately, not every variable conforms itself to the bell curve. And so things that are naturally skewed in the environment often get forced and jammed into a model that uses the bell curve when they really don't fit it. But by and large, most variables fit the bell curve. Most of the time you have a symmetrical distribution, and you have a clear mean in a sample, and then you have people that fall below it and above it in more or less equal numbers, forming this characteristic shape. Okay, now we're going to go through its properties, its mathematical properties, just some of them right now. We'll be using the bell curve all through the course, but we're just going to start with some of its basic properties and then work our way through very methodically through other properties and other applications of the bell curve. Okay, you see here that there's a z-scores at the bottom here, which are kind of small, but you can see the middle one is 0. That would correspond to the mean of the sample of the distribution. And then you see z-scores going up and down by whole units, 1, 2, 3, 4, or -1, -2, -3, and so on. And each one of these z-scores is associated with an area under this curve. And the area is defined by a percentage of the curve. So you can see that the area between the 0 and the +1 z-score is associated with a part of the curve that's 34% of the curve. So 34% of the normal curve lies between those two numbers. And as you see, as you go up the scale, or go toward the extreme ends of the scale, the percentages go down. So the next unit between 1 and 2 has 14% of the curve. And then finally, curve that's above 2 z-score units is 2% of the curve. Now, that's a very important property of this curve. It allows you to use it for all kinds of cool things. All kinds of interesting ways of calculating standard scores are derived from the areas under this curve and how much is there. And you may recognize, if you've taken standardized tests, that sometimes they're expressed in terms of percentiles. And that percentile score corresponds to these percents you see here. But now also this curve is used to calculate probabilities. And if you think about probabilities, you can think that they're often expressed in terms of percentages. Okay, but the thing to remember from this slide is the characteristic shape of the curve. It's associated with area under the curve, and those areas have a very characteristic symmetrical percentage basis. So as you go up the scale, the z percentages under the curve are the same as when you go down the scale. That makes the curve symmetric. The normal curve. Okay, now we're going to go over how you calculate percentile scores using the normal curve. You remember from the previous slide I was talking about percentages under the curve. Well, you can actually use those to calculate what's referred to as a percentile. And a percentile represents the percentage of people that a certain raw score, the percentage that's under that score. It could be framed also as a percentage over that score. It's usually framed as the percentage under that score. So if I score in the 98th percentile, that means I score better than 98% of the sample. It also means obviously that 2% of the sample scored better than I did. And a lot of times you see standard scores expressed in that way. It gives you a common sort of metric to place the scores on, rather than thinking of them in terms of a z-score of 1.57 or even an SAT score of 630. You just express them as represents the standardization expressed as a percentage. The percentiles represent a score above or below a certain raw value. If you go to the web, there's a nice little applet at a website that's referred to here. I hope it's still there. Sometimes, web links come and go. This web link has a normal curve under it, and what you do is you move the cursor underneath the curve, and it will give you a continuous readout of how much of the curve that is subsumed by how you moved it, and what the percentile is, therefore, that corresponds to that area. So I encourage you to go play with that, and also it will help you calculate percentages and check on the percentages that you calculate using other methods. Okay, so for this part, first of all, think about your SAT scores. Took the SAT, you probably got a score, which comes to become an indelible part of your character now. Somehow your SAT scores and the SAT scores have taken on a life of their own. As I recall, the SAT score had a normalized mean of 500 and a standard deviation of 100. And so if your SAT score was 600, what is your percentile? And just think about that. We're going to, actually calculate that using different methods. But think about what that would mean. Okay, the mean is 500. The standard deviation is 100. What would be the percentage of people that scored 600 or less? The normal curve. Calculating percentages. Okay, now we're going to calculate a percentage using an estimate approach. And this you could do if you just needed a quick, sort of a quick and dirty estimate, or if you knew you had a whole number. So if you knew you had a whole number in terms of the standard deviation units, you can pretty much just estimate it if you remember roughly how much of the curve is under each number. Okay, so here you got the normal curve. Your z-score is 0 is the mean. Standard deviation, one standard deviation unit away from the mean is 34% of the curve. 2 standard deviation units away from the mean is not 14%. That's between 1 and 2. If 2 standard deviation units away from 0 would be 34 plus 14, which would be 48%. Okay, so imagine you had a standard score that was 1.5 standard deviation units away from the mean. Say it's a z-score of 1.5, or whatever the score is calibrated in deviation units. Again, if it's an SAT score, remember an SAT score has a mean of 500 and a standard deviation of 100. So a score of 650 would correspond to a z-score of 1.5. Now, if you look at the curve here, you got 34% plus half of 14%. So that would be 7%. So 34% plus 7 would be 41%. So 41% of the curve is between 0, the mean, and 1.5 standard deviation units above the mean. Okay, you're not done yet. You've just calculated the difference between the mean and then 1.5 standard deviation units above it. But you got the rest of the curve below the mean to also account for in terms of the number of people that would have scored below 1.5 standard deviation units above the mean. So you've got to add 50% to that. So you got 41% for the right half of the curve, and then 50%, of course, for the bottom half, giving you 91%. So in this case, 1.5 standard deviation units above the mean corresponds to the 91st percentile. And practice that with a few scores. So going back to our SAT score, where we had an SAT score of 600, an SAT score of 600 is 100 units above 500, which is the mean for the SAT. 100 is the standard deviation. So a score of 600 corresponds to 1 standard deviation unit above the mean of the SAT. Well, again, go to the curve here. We notice that between 0 and 1 is 34%. But then we've got to add 50% for the remainder of the curve that's below the mean. So we take 50 plus 4, and we get 84%. So a score, an SAT score of 600 corresponds to the 84th percentile. Somebody who scores a 600 scores better than 84% of the sample. And of course that means that 16% of the sample still scored better than that person. But you can see how you can make a pretty good estimate, of a percentile, sort of quick and dirty, using a rule of thumb. And if you just keep in your head that the major demarcations of the z-score at 1 and 2 would correspond to 34%, 14, and 2%, then you'll have a pretty good idea what a percentile is without having to use some sort of calculator or going to a table that has percentiles in it. So you can make a rough estimate if you just keep in your head 34, 14, 2. And sometimes you'll see in a movie, I think, in the course, a reference to another rule, which I can't remember the numbers off the top of my head, but it's the same type of thing where they've demarcated the curve according to some whole percentages that would be relatively easy to memorize. The normal curve, estimating percentages. Okay, probably the most common way to get percentiles is to look them up in a table of some kind, where all the different percentiles corresponding to different z-scores have already been worked out. These days also computers are used, and SPSS probably has a way of calculating percentages. They amount to converting, basically what a normal curve is a, it's a curvilinear shape, and to get the percentile for a z-score, you have to calculate the percent of the curve it's at that point and below, and to do that you need to use some calculus to get the curve calculations correct. Some people have that built into computer programs, though, and it's relatively easy to do. It's not something you can easily do in your head, though, for very specific numbers. The tables that have been constructed are probably, close enough for most applications of percentile, and that's the method that I'll show you now. Okay, what we're going to do is do the same thing we did before, looking up a percentile score, calculating one from a raw score, and here are the steps involved, and we're going to use a table. So step one is you take the raw score and convert it to a z-score. So say you've got a raw score, say you've got a sample with a mean of 100, standard deviation of 15, like an IQ score. Somebody scored say an IQ of 115, just to make it easy. So you've got a mean of 100, standard deviation of 15, and somebody scores 115. So now we've got one standard deviation unit above the mean. That's the z-score. So the z-score that corresponds to 115 for IQ is a 1, because that's one standard deviation unit above the mean. Step two, you draw in the normal curve in the shaded area. Do that if you are good at drawing. It's good to conceptualize it, I think, graphically, because that helps you remember which side of the curve you're on, and that helps help you remember to add in the 50% for the lower part, if that's what you have to do. If it's a negative z-score, remove the negative sign, because tables are not usually constructed. Since the distribution is completely symmetric, you don't need a table for the whole curve. You just need a table for half the curve. Add 50% is appropriate if you're above the mean. Okay, then you use a z-table to convert the z-score to the percent away from the 50% mark, and that just means 50% mark is a z-score of 0. And when I show you the table, you'll see what that means. And then you convert the value to a percentile, like we did before. The table is going to have very specific numbers in there, so it's going to have, a z-score of 1.23 corresponds to a percentage of, that would be something like 40.5% or something. But we'll see that in the table. So basically what you're going to do is take your z-score, once you've calculated that, go to the table and find it. You're going to add 50% to the percentile you see in the table if the z-score is above 0, and you're not going to add % if the z-score is below 0. So let's go to the next slide and take a look at what a table looks like, and I think you can understand better what I'm referring to. The normal curve, calculating percentiles. Okay, here in this slide you see a z-table, which I referred to before in the previous slide. And you can see a z-table has columns of z-scores and columns of percentages to the mean, which is a z-score of 0. And you can see in the first entry there that a z of 0 has %0 associated with it. naturally. And as the scores go up, you see more and more of the curve being subsumed by the difference between 0 and the number you've looked up. So let's look up a z-score. Suppose we figured out, okay, our raw score corresponds to a z-score of 1.16. So it's 1.16 standard deviation units above the mean, and that corresponds to a percent to the z of 0 of, if you look down here at 1.16, it's a percentage of 37.698. Okay, so that's the percentage of the curve that's between 0 and this number. But remember, you've got the whole bottom of the curve that still corresponds to the people who score below this number. And so the bottom part of the curve or the bottom half is 50% of the curve. So I take 50% and I add it to this number. So that gives me 87.698%, and that's my percentile for a z-score of 1.16. Now you can see right away this table has given you a much more accurate number. You've got 3 decimal points here, and you may not need accuracy that high. But you can see where a table is giving you much more accuracy than the rule of thumb would give you. Okay, so that's a z-score of 1.16. Now imagine if you had a z-score that was, just to make it simple here, a z-score of 1 that was 1, let's say it's -1. It's 1 standard deviation unit below the mean of 0. Well, actually a 1 is not actually in this. It was 1.02. And we know from our rule of thumb that a z-score of 1 corresponds to 34% toward the mean. But now this is 34% below the mean. So the percentile of people that scored worse than that person who scored a z-score of -1 is going to be a relatively small percentage compared to these ones we've calculated already. And we know it's 34% down. If we take, okay, that's 34% down to -1, 50%, which is the upper part of the curve, it's above 0, giving us 84. Now that's not the percentile. That would be a percentile corresponding to 1 standard deviation unit above the mean. But one that's 1 standard deviation unit below the mean, I then take that 84 and subtract it from 100. And that gives me a percentile of 16. So a z-score of -1 corresponds to a percentile of 16. But 16% of the sample scored below that number of -1 z. Which for, say, for an SAT score, again, SAT scores have a mean of 500 and a standard deviation of 100. 1 standard deviation unit below the mean is a 400. So a SAT score of 400 corresponds to a z-score of -1 and a percentile score of, 14? Let's do that again. No, it's 16. So it's 34 plus 50, subtracted from 100, gives me 16 percentile. So an SAT score of 400 is in the 16th percentile. So that person, if you scored that way, scored an SAT of 400, that means that you only beat out 16% of the sample. And you can see, obviously, 84% of the sample scored better than you. So an SAT score of 400 is a reasonably low score. Again, an SAT score of 400 corresponds to a z-score of -1. And you can then use the z-table here to calculate the percentages in the percentiles. Again, you can see how percentiles are quite handy. You know, every score can be converted into one. So if I have an SAT score or an IQ score or any kind of standard score, I convert it back to a z-score, then calculate a percentile. And when I report the percentile, it conveys a lot more information usually than just the raw score or the standard score. Because I've told you how many people scored above that person, how many people scored below them. And often that's very compelling information depending upon how you're using the score. The normal curve, percentiles. Well, you can always go backwards from the percentiles to the actual scores. So if somebody says, well, I scored in the 40th percentile on the verbal SAT, what would be your score? Well, the tables aren't exactly designed to calculate backwards, but you could use them for that. You would go back to the table, look at the percentile that corresponds to the 40th percentile, and that's going to be, a 40th percentile will be 10% below the mean value. Remember, the z-scores go by the percentage away from 0. So you go to the point where it says, well, here's 10% away from 0, and that will correspond to the z-score. Then you convert the z-score back into a standard score or to a raw score, depending on what the standard deviation was. So again, say with a SAT score, if I scored in the 84th percentile, that would correspond to a z-score of +1, and that would then be a score of 600 because the SATs have a mean of 500 and a standard deviation of 100. I don't know many applications where I've done this in reverse, but of course you could. It's very unusual to have the percentile reported without having the standard scores reported ahead of time. Usually when you score tests, you score them, you don't score percentages, you score them based upon the scores of the test and then convert those into percentages. But if you had percentages, you could convert them. I mean, the point of this really is that the logic of this is that the percentile is just a conversion of the z-score or the standard score or the raw score once you know what the mean and the standard deviation is of your sample that was used to base the scores. And you assumed that the scores distributed according to the normal curve. So the normal curve percentages are what you're using to make your conversion, and you're assuming that your test scores correspond to that. The normal curve. Okay, well, one interesting application of the normal curve is in conceptualizing an interesting phenomenon that's occurred in baseball through the years. If you're familiar with baseball, you know that your batting average is an indication of how often you make a hit when you come up to home plate. And if you're batting 500, that means that you make a hit every other time you come up. You make a hit every 50% of the times you come up to bat. Well, a really good batting average is 300. For excellent batting average is 400. Most professional baseball players would probably have batting averages between the range of 250 and 300. But back in the 60s and before that, there were a number of players that had batting averages of around 400 or so. And in modern times, this has not occurred. It's been this sort of great mystery that all the baseball pundits have tried to figure out. Well, it turns out it's just a statistical phenomenon because of the way batting averages are calculated and the way that the standard deviation has shrunk. There's less variability among hitters now than there used to be, and that less variability has resulted in fewer hitters getting a high number of hits when they come to bat. At any rate, the movie explains it all. So go to the course website for this unit, and you should see a link there to a movie called Batting 400. The normal curve and probability. Well, you may recall that I mentioned that the normal curve can be used to calculate probabilities in statistics. It is the basic probability engine for statistics. The normal curve represents a distribution of outcomes for a study, as well as a distribution of scores from a sample. And the dispersion of the normal curve and things like it allow us to calculate probabilities for different outcomes. And when we actually calculate statistics later on, we're going to calculate the likelihood, say, that two means are different. And to determine that likelihood, that probability, we're going to turn to the normal curve. Well, to understand this idea of how the probability can be calculated from the normal curve, I think you need some introduction to probability itself. I'm sure you've heard of probability. I'm sure you've used it from time to time. Anytime you do a gambling game, you're actually engaged in a probability judgment. So if you flip a coin to see who's going to play first in a football game, or if you go to a casino and play craps or play blackjack or poker or any of those games, they're all related to probabilities. And what you're basically doing is, hoping. It's like a big lottery. You're basically hoping that the outcomes that result in an advantage for you come up. And they're usually, the gambling houses have games that favor them. And on average, when bets are made, the gambling establishment is going to make its cut sort of no matter what. But essentially what you're doing when you're gambling is you're trying to beat the odds. You're trying to do better than what we predicted based upon chance alone. And there's a fundamental belief that somehow some light from heaven is going to shine on you to enable you to do better than chance. Okay, well, I'm just going to give you an introduction to probability, and then we're going to go back to the normal curve and talk about how the normal curve is a probability function. Okay, basically probability is a calculation of a contrast between the single outcome versus all the outcomes that can occur. And they're given special names, these outcomes. So if you have something like a coin toss, or if you have something like a die here, you can see in this graphic, you see both of those. If you look at a coin toss, coins are heads or tails. You have two outcomes. If you have a single die, you have 6 possible outcomes, 1 through 6. And what you're going to calculate for the odds for the probability is a ratio of these things. And first you need to understand what the relative frequency is. Well, the relative frequency is the number of times something happens relative to the number of times it could have happened. So if you think about all these are even, what would you call them? They're sort of balanced probabilities in the sense that there's an equal chance of getting a 6 as there is a chance of getting a 1. There's an equal chance of getting a heads as there is of getting a tails. The expected relative frequency is the expected outcomes if the experiment is run numerous times. There's a famous case of an American prisoner who had nothing else to do after he was in prison during World War II, and he decided he was going to flip a coin, as many times as he had time for, and he would flip the coin all day. And he kept track of how many times it was heads and how many times it was tails. And he flipped the coin something like, thousands and thousands of times because he was in prison for years. And he actually calculated in the end, how many times a coin toss is exactly 50%. He discovered that it's slightly off 50%. That however he was tossing the coin produced a bit of a bias. It wasn't very big, but it produced a small bias in the coin tosses, which is a lesson for all of us, I think, that we think of coin tosses as being completely random, but actually ways of tossing a coin so that over thousands of coin tosses, you might actually see a preference. The normal curve and probability. Okay, let's calculate some expected relative frequencies and some probabilities associated with some simple coin tosses in the roll of a die. Remember, the probability is expected relative frequency of a particular outcome. And here's how you calculate it. You calculate the probability equals possible successful outcomes divided by all possible outcomes. So you should remember that equation. And you probably have used it in the past. Whenever you've talked about the percentage of something happening, or when they tell you the odds of winning the lottery and things like that, they're actually giving you this ratio. Okay, so for a coin toss, you've got two options here in a coin toss, heads or tails. So the probability of heads can be calculated as heads is 1 possible outcome, and all possible outcomes is just 2. You can either have heads or tails. So you can take 1 divided by 2, that equals 0.5, which is translated into 50%. For probability statements. With a die, you've got 6 possible outcomes, so that's all the possible outcomes. And you've got 6 individual outcomes, so 1 or a 2 or a 3 or a 4 or a 5 or a 6. So for example, what's the probability of getting a 1? Well, you take 1 divided by 6, that equals 0.17, and so the probability is 17%. Of getting a single number on the throw of 1 die. The normal curve and probability. Okay, let's try some other examples that are a little more complex, so you have a feel for how probability can be used for more complex judgments. In most gambling games or the lottery, it's essentially 1 outcome divided by all possible outcomes. Well, you can do this more complex. Suppose you're going to consider more than just 1 outcome. Well, in that case, you calculate the probability slightly differently. The probability equals the possible successful outcomes divided by all possible outcomes. So imagine you're going to roll a die, and you're going to get paid. There's going to be a payout if you roll the number 1, 2, or 3. There's not going to be a payout if you roll the numbers 4, 5, or 6. Well, now you got to think about that. What's my pay? What are my odds now? I'm going to get a payout for 1, 2, or 3, and not just a single number. Well, you take the number of possible outcomes that are successful. In this case, it's 3, 1, 2, or 3, and divide by the total or all possible outcomes. So there are 3 outcomes that are successful. There are 6 total possible outcomes. So your probability equals 3 divided by 6, which is 0.5, which is 50%. So now your odds are much better. Getting a 1, 2, or 3 is 50%, whereas before we discovered that rolling a single number, the probability of that was 17%. So you can see how probabilities change with the number of outcomes. Normal curve and probability. Okay, well here's a slide with some even more complex outcomes and more complex examples. And they can get very complex even further than this. These are just examples to get you have a feel for what probability calculations can be like and how complex they can become. Here we've got multiple outcomes, and here it's much more like statistics. So it's a probability sort of question that's related to sampling, which is something that we'll learn about as one of the fundamental processes involved in statistics, calculating statistics. Okay, well, remember number probability, the calculation is the number of possible successful outcomes divided by all possible outcomes. And here's an interesting question about probability. What is the probability of selecting a senior from a class of 200 that contains 30 seniors? So imagine you're going to somehow pick at random from 200 people a single senior, and in this group of 200, you know there are 30 of them somewhere in the sample, somewhere in the group. Okay, well, there are 30 possible outcomes, possible successful outcomes. If you pick one of those seniors, one of those 30 seniors, that's a successful outcome. However, there are 200 total possible outcomes, 30 seniors plus the 170 other students. So you've got 200 to pick from. That's 200 of your possible outcomes. You could pick any one of the number 200. So when you calculate your probability, it's 30, which is the number of successful outcomes, divided by 200, which equals 0.15, which is 15%. So if you're going to try to find a senior, 30 seniors in a group of 200, your odds of doing that are 15%. So 15% of the time of the choices that you make will be a senior, and the other 85% will be other students. Probability in the normal curve. So here in this slide is a summary of what we learned about probability so far. It's important to keep these points in your mind as you think about the normal curve and using it for probability judgments. Okay, first of these is that probability is a proportion. It represents a division. It ranges between 0 and 1, so probabilities are always expressed as between 0 and 1. They're often expressed as percentages of the interval, and so you often hear probabilities being 50% or 100% or 80% or 95% or 5%. Now, probabilities in statistics are often expressed in ranges using less than and greater than. And a very common expression of probability in statistics is probability P less than 0.05. You'll hear that over and over and over again. And what that means is the probability range is 0.05 or less. So it could be 0.03, 0.01, and so on. And what you've expressed here is a cutoff of probability at 0.05 or 5%. Probability in the normal curve. What you see here is a set of slides, 2 slides that are going to depict what happens when you don't have symmetry in your bell curve and how that might affect a probability judgment. So look at this curve here. This is a relatively normal shape here. You can see ghosted behind the histogram is the normal curve, and this system of histogram blocks almost matches it. So you have basically a bell-shaped curve, a bilateral curve. It's bimodal. It has approximately the same number of people below it, below the mean as it has above the mean. And you can see where the numbers trail off precipitously as you go away from the mean. Ask this question as it refers to probability. What's the probability here of selecting a person with an IQ greater than the mean compared with the probability of selecting someone with an IQ less than the mean? And if you were to actually select in things or perform the calculation, approximately half the number is above the mean and half the number in the sample is below the mean. So the probability is the same. If you were to pick someone at random from this distribution, then the probability is approximately the same that you'll get somebody above the mean as you would below the mean. So the probability is 50% for both those successful outcomes. And that's because this distribution is symmetric. And I'll show you a slide next in which the distribution is not symmetric. But here you see the probability would be approximately 50% for picking somebody at random and having them be above the mean or below the mean. Probability in the normal curve. Now here you see the second slide in this series, which depicts an obviously skewed distribution. So if you look at this distribution, in which there's a strong positive or right skew, ask yourself the same question about probability. What's the probability of selecting a person with a salary greater than the mean compared to the probability of selecting someone with a salary less than the mean? And here the mean is approximately $34,000. And if you look at this distribution, you can clearly see that the number of people above the mean is different than the number of people below the mean. So the probabilities aren't equal. If you were to try to use this curve to base your probability judgments, you wouldn't have an equal dispersion of probabilities above and below the mean. The probability judgments would be off. They'd be biased in a certain direction depending on what you define as a successful outcome. But here clearly with the skew distribution, you've now deviated from the probability judgments that could be made using a normal curve. And this is why when you actually do a study, you have to maintain the assumptions of the normal curve, because that's what probabilities are based upon. Probability in the normal curve. Okay, well here we see the normal curve again. And we see it depicted in its very classic form. And we're going to treat this curve as a probability density function. And what that means is the curve is a depiction of the range of probabilities for different outcomes. So now instead of thinking of it in terms of a distribution, simply a distribution of scores, we're going to translate it into the probability of achieving certain scores. Okay, so if you've got a normal curve like this, like with the IQ data, your scores and your percentages represent not just z-scores and not just percentiles, but they can actually represent the probability of achieving scores in those ranges or at certain levels. So let's take a very simple expression of this. Okay, the proportion of scores between any two z-scores is the same as the probability of selecting a score between the two z-scores. For example, the probability of a score being between the mean and plus 1 z-scores is 0.34 or 34%. In a probability density function, the area under the curve represents the probability of scores in that range. So if we have a score in the range of between 0 and plus 1 standard deviation units, or 0 and plus 1 z-score, that subsumes 34% of the area underneath the curve. And the probability then of getting a score in that range is 34%. So think about it. What's the probability of getting a score between a z-score of 2 and a z-score of 3? Well, that probability is approximately 2%. And you can see with a normal curve, the probability of getting scores around the mean is relatively high. So between minus 1 and plus 1 z-scores, you have 68% of the curve. So the probability of getting a score in that range is 68%. The probability of getting scores more toward the tails is much, much less. You can also take this logic to the probability of getting a single score. And the probability of getting a single score of, say, 1.5 is represented by the area under the curve at that point. And that's calculated using calculus. You can find these probabilities for individual points in z-tables. Right now, though, we're just concerned with the probability of ranges of scores and those probabilities that I've just described. This slide has a simple instruction to go view two movies. These are at the course website for this unit. So go there and download the movies and take a look at them. They're both really good examples of the binomial distribution and probability judgments based upon it. The normal curve and probability. Here we see an example, a depiction of the application of probability in statistics. And it has to do with sampling. Sampling is a reference to a set of methods that involve taking subsets of populations and then making inferences based upon these subsets. And samples are something that are endemic to statistics. It's something that's done all the time. And there's a probability judgment involved when you take samples, and here you see it expressed here. Suppose you have a population of jelly beans in the world, and you're going to go out and sample, say, 100 jelly beans at a pop here that might be in a single bag. Well, if you went out and did that, you took samples from the population of jelly beans at random, what are the odds of getting a bag that contains only the red beans, only red jelly beans? I mean, think about that. Imagine if they were randomly distributed by the factory, and you went out and took random samples. It would be very unlikely for you to find a bag of 100 containing only red beans, only red jelly beans. That would be very rare and unusual, and the probability of that is extremely small. Well, you can see where once you frame it this way, if you're talking about, say, taking a sample of people to do a survey, or a sample of people to do a treatment outcome study, or a sample of people with certain kinds of illness or psychopathology to do a study, you have to evaluate the probability of those people getting in the study, and of course it should be equal. Everybody should have an equal chance in the population of getting in the sample. If certain jelly beans have an unequal chance, then you'll end up with a bag of beans thinking that it's a random sample. Samples and populations. We use samples to make inferences about entire populations. What are some of the major areas in which samples are used? Well, here I have reference to a basic sampling movie. Go and watch the movie. It explains how sampling is used in a variety of ways. You may be surprised at some of the applications of sampling that you may not even be aware of. At any rate, go play the movie and then come back to the presentation. Sampling and populations. There are a variety of different ways of collecting samples, and samples are subsets of a population. You want to collect samples in a way that they represent the population. Well, they're not going to represent the population if they're collected in some biased and non-random way. You want to collect a random sample that's large enough to represent the parameters of a population and not have to expend all the resources, to actually measure a parameter in a population. That might be impossible for some things. And so you want to take a random sample to represent the population and use the information from that sample. Well, the hallmark of this is randomness. In an ideal situation, you've got a population, you've got a sample. Every member of the population has an equal chance of being selected, has an equal probability of entering the sample. Well, there's some other ways of doing this. There's stratifying the samples. The domains really represent other populations, but sometimes they're really subsets of a population. And you want to make sure that everyone gets sampled. And so what the investigator does is stratify the sample or the population into areas that are going to be sampled to make sure that he has an adequate sample from each one of the subtypes that he's trying to examine. All kinds of stratification, though, represent a kind of bias. You have to be very careful when you use it. Essentially, stratification is representing a populations instead of a single population. And so when you stratify by, say, levels of education or making sure you get the same number of men and women in your sample and things like that, you're stratifying them. So you take a random sample of men and a random sample of women. What you're actually doing is sampling from two different populations, a population of men and a population of women, and you're calling that stratification. A lot of us do this. It's a way of trying to make sure that the sample is representative of the population. My opinion about it is that stratification always introduces some kind of a bias. So you got to be very, very careful about how you do it. And in some situations, I don't think it has much influence on the results. In other situations, I think it does, and should be avoided in general. If you can make the same inferences or make the same statistical test without stratifying the sample, then you shouldn't stratify. Use a plain, clean, random selected sample without any kind of stratification or preconceived selection bias. Now, there are practical mechanisms for actually creating random samples. You have to do something to get your randomness. The game of bingo is a good example of random selection. Lotteries are random selections. And what you want to do for random select for surveys or psychological studies is to essentially assign people a number, and you have a random number generator pick from that sample, like in a bingo game. In a bingo game, all the balls are assigned numbers, and through the actions of the spinning wire ball there, you have this dispersion of the numbers across the sample, the population. And so when you pick individual numbers, you're going to be picking them at random. Okay, now I want you to play a movie called Stratified Sampling. Go to the unit website and you'll see the movie listed there. Click on the link and you should be able to see the movie. It has a nice description of stratified sampling and how that's done, and you'll get a feel for what I was talking about in terms of selecting subgroups from a population. Okay, sampling versus populations. This is a slide that depicts the differences in really labeling population parameters versus sample statistics, and makes a clear distinction between those two types of metrics. The descriptive statistics that we've learned so far, the mean, the standard deviation, and so on, are called sample statistics in the context of making inferences. So you're going to make inferences about a population from samples, and so there needs to be a demarcation of what the mean of the population is versus the mean of the sample, or the standard deviation of the population versus the standard deviation of the sample. And here you see depicted the different symbols used for each one. Notice that the population parameters are referred to using Greek symbols. So you have mu and sigma. And the sample statistics are referred to using the Roman letters. Notice that the variance also has a square sign next to it. The variance is the square of the standard deviation.